speaker while Sourav is setting up. So Sourav comes from NTU, which is relatively near to my university in Singapore. I've known him since 2001, since I go back to NUS. I know we got for us graduated here, but we have been knowing each other for a long time. He started with bioinformatics and still working on bioinformatics, network, graph, etc. He has got various best paper awards from CICAM 2004 and 2011. And recently, if you really want to look for a good proceeding chair, he got the best, one of the best service award, PLDB service award for doing a very good job at the proceeding. He likes to draw, so this is one of the pictures I have on my stage. Okay, so let us welcome Sourav.
Thank you. First of all, thanks Reno for inviting me. Great pleasure to come to University of Hong Kong for the first time. I've been coming to Hong Kong several times, but I always land up in HKPU, in Byron's office. Okay, so the slide you're seeing is the building you're seeing. It is, I think, very appropriate in Hong Kong because this is a part of NTU's lecture theaters and tutorial rooms. Its official name is Hive, but its local name is Dim Sum Building because it looks like a dim sum factory. So I thought this may be very appropriate. I'm going to talk a little bit different from many of the previous speakers, but resonating something with Kevin Chen's talk. So let me start by giving an overview of the world of graphs. So we all know that graph data is ubiquitous now. There is a lot of talks on this, and then Renaud also talked about this. So let's say who are using graphs. So of course, first thing comes into our mind is all these big, massive social networks, the web, the collaboration networks, and so on. So the people who are really interacting with this graph in these organizations are really techies. So you give them any programming languages, they will pick it in a fly. Who else uses graphs? It turns out there's a lot of people who uses graph structured data. They might not know they are called graph structured data, but security analysts, biologists, pharmacists, social scientists, even ecologists, financial analysts looking into financial networks and so on. They're all interacting with graphs. And all these people do not know how to code. Many of them do not want to learn how to code. And they simply want to get this information from the data to do their job they're supposed to do. Okay, now let us see how database folks interact with graphs. We love query languages, and Kevin already highlighted a bunch of query languages for structured data. And this is for graph. This is a language called Sparkle. And we don't teach graph query languages at undergraduate level. So it's not as prevalent in a computer science course at undergraduate level if you consider graphs data. Okay, so, and if you see this language, this is from the keyword, it's asking questions over protein-protein interaction networks in the biology domain, but this is very hard for any biologist to learn. They don't find any need to learn in order to learn. So the learning curve is steep. And if you ask people to use this, they're not going to use it. So our first point of access to a graph data management system is a query language. And that is where we break. Because you've got to learn this before you can access the data. You can give the fastest data management technique, algorithms inside your black box, but in order to use that, you've got to know how to learn. First of all, write a query. Now, on the other hand, Ben Schneiderman said that classic code was computing time and power is getting cheaper, but user's time isn't. So if the user wants to spend on learning certain language, it is expensive. Okay, many people say that expensive servers are cheaper than expensive programs. Okay, now, so are we nice? Data management community, are we nice to our end users? It looks like that we are very nice to machines. With the modern hardware, we have adopted all our algorithms to exploit the modern hardware as much as we can. Okay, we are very nice nowadays to DBAs and the database providers and cloud providers and all that. You saw in the morning when Fefe talked about self-driving databases, self-driving codes. Okay, so we are very nice to them. But are we nice to our end users? People who are supposed to write queries. Okay. So it turns out our leading and very distinguished database scientist is aware of this problem long time back. In 2005, this is the 5 years database research self-assessment report, which happens every 5 years, and very distinguished scientists in our field get together to chart out what's the problem they're going to look in the next 5 years. And it was in 2005, so those are the great days for XML. And they used this, said it has been documented that end user will not learn SQL. Rather, SQL is a notation for professional programs. And if you just replace SQL with graph query language, this still holds. So the warning was sounded way back in 2005. But it turns out not many people were paying attention to it, so they again warned in 2016 meeting. In a different language, but they're trying to say the same thing. Today's data consumers may not know how to formulate a query at all. Our user base has evolved. What kind of users we had in the 80s, in the 90s? They are technically much more expert in writing queries. That user base has changed. So we have modified our algorithms when our modern hardware changed, but we have not really modified our paradigm with the change in users' profile. So at this point of time, we say, okay, these guys are all scientists. They sit in ivory tower, they don't go and write codes in companies and all that. They might not know that, maybe the practitioners are very happy with all this. They don't mind query languages at all. So let's take a look at what happened in last VLDB. VLDB, this is 2018, best paper in VLDB. It was a survey of what practitioners and researchers think of graph data management problems. So they surveyed 53 practitioners, out of them 36 are from IT. So large fragment of them are working in IT field. So you expect them to know something about programming. It turns out that one of them, taking the quotes, really quotes from the paper, the overwhelming majority of the emails and issues were routine engineering tasks, such as users asking how to write a query. So you're coming back to the same problem. Users are having trouble writing queries on graph data. Mind you, this is majority of the 36 out of the 53 are still IT professionals. So if you just take non-IT people, this problem exacerbates a lot. So they found out what are the top 10 graph computation challenges, and right up there you can see query language and usability comes in the top.
Who is the recipient and who is the sender? Who is talking about whom is talking?
So these guys took a survey, and these are the users' feedback, what the users think about. So these are practitioners as well as users. So the authors are mentioning that this is what they are talking about. Okay, so this is a quote, unquote, from the paper. Okay. All right, so the paper is, the reference to the paper is right there. Okay? So, one way to alleviate this problem is to look into SCI. And SCI has, if you take a classic textbook of SCI, you'll see there's something called direct manipulation style of interactions, where you basically visually present task concepts. It's very easy to learn, easy to retain. You make less error. Naive users, intermediate users, expert users all can use it. And simple example is your Windows has a lot of these direct manipulation. When you delete a document, drag it and drop it in the bin, that is basically direct manipulation style of interactions. Now, does real-world graph querying system use this kind of interaction? So it turns out there are two I would highlight here. One is from PubChem, and another is from DrugBank. Both are commercial systems. Both are available on the web. Both are for querying large collection of chemical compounds. So each compound is basically a data graph. Okay. Both provides a direct manipulation interface. In short, it's called visual interface as well. Okay, interesting thing is, you might think, okay, they quoted, this is one of the alternatives. Other alternatives may be a query interface where you can formulate the query using Sparkle or any graph query languages. It turns out they do not provide any interface for writing queries in a graph query language. They allow you to write queries in a string of a chemical compound name and so on, but nothing on a graph query language. Okay, so basically they got a probably better feel of their customers and the users, and they think that it is not so appealing to ask users to write queries using this query language. So at this point of time, we can just say, okay, that's not a problem. You can have a graph database. You can slap a particular data direct manipulation style of interaction interface on top of it, and then you can ask the users to draw their queries in an intuitive style, drag and drop manner, and then run the query. You formulate the query and then click run, and the query is sent to the database, to the underlying database. You might internally transform them into a particular query language and execute the query and then return the results. So this is a traditional paradigm actually, if you want to build a direct manipulation based style of interaction. Okay, and here there's a clear separation between query formulation and query processing. So query problem formulation is basically then becomes a domain of ACI, and query processing becomes a problem of database people. And we typically focus on this. A large number of papers always focus on this. We don't care much about that. So can we do more than this? Can we integrate these two? Because remember, when you're doing a direct manipulation, you're actually giving hints. Okay, and when I draw this, I'm looking for something in the data which has this particular pattern. And then when I add some another pattern, then I'm looking for something which has both these patterns. So as we progressively draw our query on the interface, we are actually telling what we are looking for. And we can exploit that as we are drawing, rather than waiting for the run button to be pressed before we wake up and start processing the query. So we want to go further by taking advantage of this direct manipulation style of interaction. So what can we do? For example, when you're drawing something, let's say you draw a part of a subgraph of a query, we can give suggestions and feedbacks based on what you've drawn. Maybe you're going to add this particular subgraph in your query again. So we can give suggestions and feedbacks. We can have a faster response time, or we can reduce the user's waiting time by whenever they start drawing, we start processing the query, because we know what they're looking for, partial fragment of the query, so we can start processing. We can also do interactive search. So once we draw, so let's say we draw an edge, another edge, two edges, and then we click the run button, we get some results, look into the results. Okay, I now expand my query based on the results, we add something more, we again look into the results and so on. We can do interactive search and exploration. We can also do interactive visualization results. When you see your results, remember a result on a large graph is like a hairball. It just doesn't make sense. No one can see what's there. So we have to find new ways of visualizing results embedded in your graph data. Typically, we don't focus much on this because we think that's not our problem, that's a visualizing community's problem, but if you send me a result I cannot see, it's of no use. So, I'm going to take one example in the interest of time, and I promise I'm not going to show you any theorems and algorithms and all that. The details of the algorithm for the one I'm going to show you, we have a video of the Sigma talk which is available in Google. You can just check it. And if you have any question on the algorithm part, you can ask me offline. Okay, so what I'm going to show you is this idea that, as I said, there's a clear distinction between query formulation and query processing. This is the standard. What we're going to do is that as we are formulating query, we ask this question, why do you want to wait? Why can't we simply start processing as user is formulating? And intuitively, you can get results earlier because we start doing the work earlier. Okay, so we have applied this idea in a bunch of different types of graph queries, and I'll give you the broad abstraction of how this thing works. They have been adopted in different different variants of this framework have been adopted for different types of graph queries. So there are two components. One is the offline component and is the online component. You take the graph data, you build some indexes by pre-processing the graph data in certain ways, depending on the kind of queries you're going to answer. And then what happens in the online is when you are drawing a query, you build an adaptive on-the-fly index specific to the query. So as you draw, you keep updating this index. This index keeps track of the candidate matches in the data graphs and so on. So when you add something more, this index gets updated and keeps going on until you click run button. Until you click run button, and then you get the final results. Quickly, okay. So let me show you this idea with a short video.
In this video, we present Boomer, a tool for blending visual BPH and exact subgraph queries on large networks. We shall demonstrate how to formulate a BPH and an exact subgraph queries and analyze their results using real-world networks. In the first example, Bob, a biologist, uses a BPH query to find out if C. elegans organism is suitable for studying apoptosis in human. The BPH query vertices in the red box are human genes that are homolog to C. elegans genes related to apoptosis. Bob is interested if these human genes interact in the same way as the corresponding C. elegans genes. First, Bob selects a database called HumanP, which is a protein-protein interaction network where the nodes are proteins and edges are the interaction between proteins. Then, he loads the index of this network and initializes the query panel by clicking the Add Query button. Next, Bob constructs the BPH query by using the labels in the HumanP database. He chooses the required labels from the list by browsing, selecting, and performing a drag and drop action. Edges are then added between the vertices. The Boomer interface allows Bob to easily configure the minimum and maximum path length of each edge.
So what's happening is as it is formulating, in the background the query has already started processing. So it's integrating both formulation and processing at the same time.
Once Bob completes the BPH query, he clicks the Run button to request for the query results. The number of partial matched vertex sets is shown, and Bob can view the results by clicking on the View Results button. Boomer displays the result in a separate
So I'll stop here in the interest of time.
vertices correspond to.
So you can see the results, and basically the whole idea is we take advantage of the direct manipulation interfaces, but we go beyond simply just slapping the interface on top of your data graph. You can exploit this by doing so. You can enhance the usability of the interface. You can improve the performance by integrating formulation and processing. You can add more functionalities by giving feedbacks and performing exploratory research to the interface. So it brings in multiple benefits of if you use this kind of paradigm of query processing. So I'll stop here because Sachin Chair is after me.